Hey, Honors Math 1 people. This is our second lesson for Monday, August 17th, or for the week of August 17th through the 21st. This lesson is called Naming Polynomials. It is not really a super long lesson, but it is some charts and things to write down. The assignment has the same name, Naming Polynomials. This assignment is not something you have to write and submit. It is a Google form with multiple choice questions that you answer. So this assignment shouldn't be too difficult to get submitted. If you have any questions, just let me know. But we're going to get started. First thing is to add this to your table of contents for Unit 1. We are on page 3. Zoom in a little bit. Naming polynomials is our lesson for the day. So I'm giving you a chance to write that down. We're going to start off with a little visual activity for me to use, so that it doesn't require you to write anything down, but I'm hoping it will help you to see what we're doing today, and then we're going to take some notes, okay? So pause the video if you haven't gotten that written, but number 3 is naming polynomials. Now first, I want to show you, I have some little cards here that have things written on them, right? Let's see, adjust my camera so you can see. Okay, so that is just a 5. So what we're trying to think about in looking at these little cards that I have for you is that we have been talking about exponents, right? And we have been looking at simplifying expressions, right? Okay, so 5 is an expression. Did you know that? X is an expression. But let me just show you. Here's, if I have 5 equals x, that's an equation, right? So the equal sign with something on the other side makes an expression into an equation. Similarly, if I had x there, if I have x equals 7 is an equation, whereas x is just an expression, okay? So this is an important place where we can kind of see if 5 is an expression and x is an expression, when we have 5 equals x, what we really have is 2 expressions that are equal to each other, right? Sometimes people mistakenly think that you just take an expression, like, let's take a simple one, 2x plus 5, and to make that into an equation, we just put equals something on the other side, right? 2x plus 5 equals 21, and now it's an equation. Now, over here, 21 is a number, but typically people don't think of a number as an expression, even though it is. It is an expression, right? By the definition of what an expression is. Okay, so now I have one here. 2x squared is the expression, and 2x squared equals 12 is an equation. I have x squared minus 3x minus 4. My thing is so there. I'll make it a little darker. X squared plus 3x minus 4 is an expression. X squared plus 3x minus 4 equals 0 is an equation. I'm looking all around. I think I've lost one of my cards. No, maybe not. X plus 4, move down because all my cards won't show at once, is an expression. X plus 4 equals 10 is an equation. And then I'm going to scooch all this up because I have one more. 5x to the third minus 2x is an expression, and 5x to the third minus 2x equals 17 is an equation. Now, we could make equations in another way. We could, let me take away all these equation ones. I could take any 2 of these expressions that I have and just put an equal between them, and now I have an equation, right? Because an equation is just 2 expressions that are set equal to each other. equations are generally solvable for a variable. Sometimes we can't solve, we can just simplify because we don't have enough information, or we have more than one variable. Now in this equation, it's important to see that although we have an x to the third power, which has an exponent of 3, and we have a regular x, which really has an exponent of 1, and over here we have an exponent of 1, we have different exponent values, but we only have one variable x, right? The value of this x is different than the value of x to the third, because x to the third power means to multiply whatever the number is 3 times, and this just means use the number. Use the regular x, multiply the x together 3 times, and use it. So x to the third is a different number than x, but it is based on the same value of x to begin with, right? So this is an equation in one variable, and that's important for what we're talking about today. We're going to talk about naming polynomials in one variable. And so what we want to get at here, first of all, is that a polynomial is really just an expression. So I'm going to take the equals away now. All of these cards that I had laid out are expressions, but we could also call them polynomials. Okay, poly means many, right? And most people kind of got that. Poly means many, but polynomial, when we're naming things, mathematical expressions with lots of parts, we need to include all numbers of parts, right? We can have one part. Okay. If this one has 1 part, how many parts do you think this one has? How many parts do you think this one has? How many parts do you think this one has? I'm asking you because I want you to try to think while we're going along here and see, do you know some of this stuff already, or is this new to you? Okay? Because the next thing I want to do is just to challenge you a little bit to think. I'm going to rearrange these and tell you that these 3 are similar. Would you agree? I would say that these 3 all consist of only 1 part, right? So even though we have a number here, which is a coefficient with a variable that has an exponent, we seem to have 3 things written, 2, an x, and another 2. It's not 3 parts to this. This is 1 part, and this is 1 part, okay? So anytime we have multiplication or division of numbers and variables, that's still considered one thing, one term, okay? On the other hand, these 3 would be considered to have 2 parts. Do you see why? Okay, when we have 2x plus 5, the 2x is 1 part, and the 5 is the other part, right? Like here's 5 is 1 part. So now we've added another part to it. X is 1 part, but we've added something else to it, a plus 4. 5x to the third is a part, and minus 2x is a part. Okay, so you can see over here, whereas this one I told you, when you have a multiplication, 2 times x squared, or even if you had a division like a fraction bar with a number under here, this would all still be one term. Multiplying by something or dividing by something with a variable doesn't change the fact that it is one number in the end, right? Okay, but adding is a little different in math, especially when you have unknowns, right? Because x plus 4 cannot be combined together in advance in the same way, or simplified in the same way that 2x squared might be simplified if it had a 2 under it. Okay, multiplication and division can go together with a variable because multiplication and division simplify each other, right, and can cancel out, but you cannot have an addition like plus 4 that will still cancel out with those multiplications. Does that make sense? Right, so this multiplication of 2 times x, we could have more than one operation and they could possibly cancel, but there's no way adding a 5 can cancel out with the multiplication and division. I hope that makes sense to you, but polynomials have parts that are separated by pluses or minuses. So this one down here has a minus. But all of these are considered to have two parts, right? Now, even though, let's separate these and think about them again, even though we said these are kind of alike in some way, they have only one part to them, they're still really different in other ways. Like 5, something I know and can count on and could do math to. If you said add 2 to it, I could do it, right? If you said, divide it by 10, I could do that, okay? I can do math to this. X, I can't really do math to it. I could write down what math you want me to do. If you want me to plus 2, I can write that down, but I can't figure out the answer. If you want me to divide it by 10, I can't find the answer. So fundamentally, these two cards are really, really different in a really important way, even though they are alike in another way, right? And so this is what naming polynomials is really based on. It's based on two different aspects of the polynomial. One of the aspects is how many parts does it have? These have one part, these have two parts. But just like the one I was just pointing out the differences between the 5 and the x over here, 2x plus 5 is a really different thing than 5x to the third minus 2x, right? This one, you only are substituting one value in and figuring out. This one, you're substituting a value in and then cubing it, and also substituting it in the other term, and that's really different here, okay? Having an exponent value with my x is really different than not having an exponent value with my x. Does that make sense? So there are differences here, even though we've grouped them in a group, there's differences here that we need to figure out how to work out. Now, these are the same because they're one term, these are the same because they're two terms, but let's look at these two. These two have a similarity. Even though they don't have the same number of terms, they have something similar about them. Okay, so if you don't see it already, the similarity of these two is that they both have an x that's getting squared, right? And that's important, okay, because when you square the number, something fundamentally the same is happening over here as it is over here. Now you got other stuff going on. After the x is squared, over here it gets multiplied by 2, and that's it. Over here, you're adding 3 times the x and then subtracting 4. So you're doing fundamentally different things after that. But that's a basic difference, a basic thing that is the same. That is the other aspect of naming polynomials. One aspect is how many terms does it have? This has one term. This has 3 terms. 1, 2, 3. So when we think about terms, these are very different. But when we think about the exponents and what is the most complicated thing that's happening to the exponent, and we would consider it more complicated the higher the exponent goes. X to the third power is a little bit more complex than x squared. X to the fourth power is more complex. X to the 10th power. The higher the power, the more complex it's getting, right? And so one way to classify polynomials is by the most complex thing that's happening to that single variable, right? And so that's one way. The other way was how many terms. So that's what we're going to write down now, is some stuff about naming. Because polynomials have 2 names. One name is based on how many terms it has, and the other name is based on the degree, right? So we're going to, I have a little heading here on my paper that I think is humorous. Okay, naming polynomials. So we have 2 dudes, and one of them is a polynomial, see? And the other one says, "What's your name, dude?" I can't ever get this camera right. It's very anti-intuitive. Okay, so naming polynomials. Do you have to write the cartoon down? No, but I think it's humorous and I like it. We have this chart. I'm just going to get to the chart and let you copy the chart because I am having the worst time with the camera again. Okay, we need 3 columns here, but I want to caution you to be careful about how I drew the columns, because this first column here is just really slim because it just has some numbers in it. This one we're going to write some words in. This one we're going to write some math in. and we're going to learn how to give our polynomials a first name and then how to give our polynomials a last name. The first name comes from the degree, and the degree is really the complexity of the exponent, right? How complex or high is the exponent, right? So the degree is the highest exponent in that problem, in the expression. So why don't you pause the video and get your chart made and then come back and we will fill it in. Okie doke. So you have your chart and we're going to fill it in right quick. We are talking about polynomials first name. Okay. First name comes from the degree, which is the highest exponent in the expression. And I have so many papers in front of me. Here we go. The degree can go from 0, and just like a lot of things, think about this, think about like wheels on a apparatus, right? Like you have a unicycle, a bicycle, a tricycle, a four-wheeler. After four-wheeler, what comes next? Five-wheeler, six-wheeler, right? Do you see how after tricycle, you kind of went to naming it by the number? And you've heard of like an 18-wheeler truck, right? So after a certain point, you just start using the number to designate it. But usually in the beginning, with the lowest ones, we have like special names for them. Like some people might call a bike a two-wheeler, but most people call it a bicycle, right? It is a two-wheeler, and we all know that, okay? So naming for the degree kind of works the same way. We could call the one that has an exponent of 0 degree, but it has a special name called constant. A first degree we call linear. Second degree is called quadratic. Third degree is cubic. So these go a little further than the bicycle, tricycle, right? We are going to go a few more numbers here before we just start using the number to name it. 4 is quartic, Q-U-A-R-T-I-C. 5 is quintic. So these two are really the same. You got to be careful. Q-U-I-N-T-I-C. Quartic and quintic. Once we get to 6, and I'm going to put a plus here because this is true for 6 and up, right? We just use the number and we call it 6th degree or 7th degree or whatever number it is above this is just called that number degree, right? So now we're going to do some examples, right? Constants, essentially, we've been talking about exponents a little, so this might make sense to you. If a variable has a 0 as its exponent, so I'm going to come over here and say, let's just say x to the 0 power, right? If you remember, that came from like having x squared over x squared. It was the same on the top and the bottom. And so what did x to the 0 power always equal? When it's the same on the top and the bottom, it equals 1, right? So when you have 0 power with an exponent, with a variable, 0 as your exponent with a variable, it makes the variable disappear because it turns it into a 1. So in a constant, there is no x because essentially the x has changed into a 1, right? So 1 is a constant. But any whole number is a constant also. Okay, I'm going to put a comma. 7 is a constant. A constant cannot have an x in it by definition because the exponent number, which is the degree, has to be 0. And so that means there's no variable, right? So when you have a degree of 1, that means your exponent has an exponent of 1. And we had said in our previous lesson that if you just have an x, that really is an exponent of 1. So anytime you have no exponent, it's really a first degree exponent and it's linear. So linear are the equations that you've been learning about a lot in math already, like 2x plus 3. So the highest degree of this exponent, 1 is the degree, right? And this is mx plus b. It's a linear equation like you've been learning about all along, okay? Quadratic equation has an exponent of 2, right? So let's say we got 3x squared. That has an exponent of 2, right? This is a quadratic equation, and it can have stuff that comes after the x squared, but it doesn't have to. Every equation, so it's named by its highest degree, which means this would be the highest one, x squared. These kinds of polynomials can have more terms after them with the lower exponents, like we can have x squared in this one, then we can have a regular x, and that's the linear term, and also a constant, right? So let's just build on this one, 2x plus 3. I'm going to add that 3x squared plus 2x plus 3. This is a quadratic equation that has all the possible terms because it can have this highest exponent and then the next one down, which is x to the first power, and then a constant, right? So every polynomial with the degree can have terms that come after it that are lesser degrees, but it doesn't have to. A quadratic equation could be 3x squared plus 3. So it doesn't have to have this middle one, it can just have these two. Or it could just have 3x squared plus 2x, that's also quadratic. It can have any combination of the terms that are lower than it. Does that make sense? So cubic would have an exponent of 3, let's say, as x to the third power. And so it can have a squared term, an regular x term, and a constant if it wants to. Or it can have any combination of those, right? So I'm just going to keep building. X to the third plus 3x squared plus 2x plus 3. So now we've built on our linear. This is the linear term. This is a quadratic term. This is a cubic term. The cubic still has cubic, a quadratic term, a linear term, and a constant term. It can have all of those. It doesn't have to have all of them. It can have some of them or none of them or a combination of them, right? But the thing that's important to make it cubic is that the highest exponent for the x is 3. Okay, so that works the same going up, but now with quartic, that has an exponent of 4. That's this number over here. So we've got x to the fourth. That's a quartic polynomial. And let's just put x to the fourth plus 5. That's still a quartic polynomial. It could have an x to the third, an x squared, a regular x, and a regular number after it. It doesn't have to. Okay? Quintic would be x to the fifth power. So let's say this one is 5x to the fifth power plus 2x squared plus 1. So this is a quintic polynomial that has a quintic term, 2 is a quadratic term, and a constant term. So a quintic polynomial can have terms after it that are all of these lower things. It can have any of them, all of them, or none of them, right? Any combination, all of them, or none of them. So that's the same as you keep going up, right? Like negative 15 x to the sixth power is a sixth degree polynomial, okay? Okay, so now we've learned how to give them a first name, right? All of these polynomials in here have the first name that they go with here, but they also have a second name that differentiates them, right? Because just like I said, a sixth power polynomial can have a fifth power, fourth power, third power, squared, regular, and a constant term. It can have lots of terms after it, but it gets a second name by how many terms it has, right? This one only has one term, okay? So when we go to naming the second name, we're talking about how many terms it has. So if it only has one term, like the negative 15x to the sixth, we call it a monomial. Mono means one. meal, right? Like polynomial, right? Nomial, right? So we're kind of working on the same prefix and suffix as with polynomials to be specific about the number, right? Poly just means many. Monomial means specifically one, right? So negative 15 x to the 6th power is a monomial. So since we have it here and here, these are its two names. Negative 15 x to the 6th power's name is a 6th degree monomial. Does that make sense? So you assign it two names based on its two of its attributes. When we have a polynomial with two terms, we call it a binomial. We have a couple of binomials over here. 2x plus 3 is a binomial because it has two terms. So 2x plus 3 would be a linear binomial. X to the 4th plus 5 only has two terms. It is a quartic binomial, right? 2x plus 3 is a binomial, and x to the 4th plus 5 is also a binomial. So two examples of a binomial, right? If it has three terms, it's a trinomial, like 3x squared plus 2x plus 3, just right here to the left, right? The same example. This is a quadratic trinomial. That's what this is called. 4 terms is called a polynomial. So 4 and up, we're going to put the plus sign there because in terms of the terms, we only have special names for the first 3, and then we just go with calling it a polynomial. Okay, so 5x to the 12th plus x to the 10th power minus 3x to the 4th plus 7x minus 1. This is a polynomial. It has 1, 2, 3, 4, 5 parts. Whoops, I'm over a little bit. 1, 2, 3, 4, 5 parts. And so that's more than 4, so we're just calling it a polynomial, right? Once it gets to so many, we just call it a polynomial. So this, the highest exponent in this one is a 12. So if we go over here to our degree, anything above 6 is just named by its number. So this right here would be called a 12th degree polynomial, right? That would be its name. Okay, let's do just a couple of quick examples and then you're off to do your homework. I'm sorry, let me go back here and make sure you can see the whole thing in case you need to pause and get something else written down. Okay, so we're going to name it, and then we're going to simplify and name it, and then we're done. Name it. Okay, see if you can do this. Let's write them both down, and then you pause and see if you can't figure out the names. There's 3 problems here, and then we will explain it and see if you can get them right. Pause and see if you can get those. Okay, so 3n to the 3rd minus 7. The first thing we do for the first name is look at the exponent. The exponent is a 3, so I look at my chart and say a 3 is cubic. So this is a cubic something. Then I look at my terms and say, okay, how many terms does it have? There's one subtraction. There's something in front of it and something after it. That makes 2 terms. That makes this a binomial. So you always split a polynomial in front of the pluses or minuses. So if I was going to make marks, I would say boom, right there, and I'd say 1 part, 2 parts, right? Next one, 6x to the 4th minus 4x squared minus 7. The highest exponent is 4, which is quartic. Now I count the terms. If I want to split it, I split it in front of each plus or minus. So right here, and then I count the parts. 1, 2, 3. So that makes this a trinomial. 9 minus 2y squared plus 6y to the fourth minus y. Now this one presents a little bit of a problem, which I wanted you to see, is that sometimes when you're getting problems like this, they're not exactly written right. When you write out polynomials, you ought to have your highest exponent first, then the exponents kind of count down until the very last term would be your number, right? And in math, we call that standard form, right? So this right here is not in standard form, and this is something that I'm wanting you to know. That's why I put it on here. Standard form means it starts with the highest exponent of the variable and counts down until the very last thing is the constant if it's there, right? So let's see, what would standard form puts the highest. Let's write this standard form just so you have it. The highest exponent first, then it counts down all the way to the constant. So when you had your little chart, right, with the degrees, that means the degrees are in kind of reverse order, highest to lowest, and the very last thing is the constant or a number that has no variable at all, right? So in this case, for this problem, if we wanted it to be in standard form, which we do, it's kind of a little mini lesson in here, the highest exponent is y to the fourth, so we would take this whole term and move it, right? It's important to remember that if you're going to split your polynomial, you can rearrange it by just moving the things between the splits. Split it in front of the pluses and minuses, then move the things. So positive 6y to the fourth goes first. Then the next lowest exponent is minus 2y squared. Then minus y. Then 9. The 9 doesn't have a symbol but a positive or negative, so it's positive. So now this is in standard form, right? The exponents are in decreasing order. Now that way we can look at the very first one and get our highest exponent is the fourth power, so that means it's quartic. It has, split again so I can see, 1, 2, 3, 4 terms. That makes it just a polynomial. Okay, does that make sense? Okay, I'm going to stop there because your homework only covers up to here. We can cover the other part of what I was going to do a different time, okay? So your homework, remember, is an assignment that is a Google form to fill in multiple choice and turn in for this, right? So that'll be easy to do and not something you have to take pictures of and upload. Okay, guys, have a great day.